This is an addendum to Chem Activity number 9, where we'll be looking at specific examples of nucleophilic substitution reactions. We'll be looking at both sn2 and sn1. It's important that you can reproduce these mechanisms to the same detail that I show you in this video. So you may want to watch the video several times. Do make sure that you take appropriate notes on a full sheet of paper and include those notes, of course, in your binder. So starting off, I'd like to look at the sn2 reaction. So for an sn2 reaction, I'm going to put the title here first of all, sn2. And note that the Sn and the N are standing for nucleophilic, and then the S, substitution. Now I'll be saying more in class about the nature of a nucleophile, as well as later in this video. But appreciate that what we're looking at here are substitution reactions. One thing is substituting for another. The two part in the nucleophilic substitution name, the sn2 name, I'll explain a little bit later as well. So let's take a look. So starting off, I'm going to draw the thing that is going to be undergoing this sn2 reaction, and I'll be including a bromine. Now we'll see that the halogens in these reactions will serve as our leaving group. So in this case, the bromine is our leaving group. It's attached to this central carbon, which will be known as our alpha carbon. On this alpha carbon, I'm going to have a 2-carbon chain. I'm going to have a CH3 group, and then I'll also have a hydrogen coming off here, but it'll be going back in the plane. Now please note that it's best when you're trying to write these mechanisms, because we need to have a tetrahedral indicated about the alpha carbon, to put 2 bonds in the plane of your paper, 1 bond coming out at you and 1 bond going away, so that indeed you can see the tetrahedral. Okay, now the other player in this reaction will be the hydroxide. The hydroxide in this case will be our nucleophile. So let me just label this guy, nucleophile. Now nucleophile means positive loving. So the word phile in this case means loving, and nucleo of course means nucleus, so it has to do with loving the nucleus. Well, what's so attractive about the nucleus are of course the protons. So this is positive loving. Now in turn, the other thing that we've drawn here is our electrophile. So in a similar way, an electrophile is negative loving. So essentially these reactions are about something that's positive loving and something that's negative loving. Now you might be wondering, why is it the nucleophile that is attracted to this particular compound that I've drawn? Well, as it turns out, we have a polar bond between the alpha carbon and our leaving group, and therefore the carbon here is delta positive, our leaving group is delta negative. So the hydroxide is attracted to our delta positive. So we've got the players all set up. This reaction is going to proceed in the following way. So I'm going to draw the curved arrows to show the mechanism. So starting from the lone pair, and I draw my arrow pointing at the alpha carbon, and then in turn I need to show that the bond between the alpha carbon and the leaving group is broken. Right? So often, or sometimes, what students do is they'll draw the hydroxide, the nucleophile. They'll also draw the electrophile, but then they'll forget to put in the complete set of arrows. So indeed, you need to show those arrows. What happens next is we show how these reactants transition to the products. So we show the activated complex at the transition state. So I start off by drawing these brackets, and then I'm going to write in part of the hydroxide, and then dash 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 line, which is going to connect now to our alpha carbon. The alpha carbon of course is attached to a 2-carbon chain. It's also attached to this methyl group, and then going back is the hydrogen, and then on the other side is the leaving group. So these dash 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 lines are meant to represent that the bond is being formed and the bond is being broken. The oxygen no longer bears a full negative charge, so we say delta negative. The bromine is starting to pick up a charge, so we say delta negative. We complete the brackets. Note that about the alpha carbon, this is actually meant to be trigonal planar, but we're looking at it from the side point of view. So it's no longer a tetrahedral, it's in transition. We represent that this is an activated complex at the transition state, in a particular transition state, by putting the double dagger. But I will label this just so that we have the terminology. So this is the activated complex at the transition state. Now sometimes you'll be asked to draw the transition state. That's not quite a correct thing to ask you, because the transition state actually represents an energy condition or an energy state. The activated complex refers to those things that are undergoing the transition at the transition state. Okay, so now on the other side, let's see what we end up with. So I've still got the hydrogen bonded to the oxygen, and the oxygen is now making a full bond to our group here. We also have a CH3, and it's coming out at us, but now it's oriented in the other way. And we also have this hydrogen, which is going back in the plane. Okay? And of course, we have the leaving group. So what I've just represented here is, in a sense, a complete representation of the mechanism, and this is what we would expect you to write if we ask you to do this. But I'd like to fill in a couple more details. So for one, let's explore the fact that I intentionally chose to use a chiral carbon, and let's see which particular configuration we started with. The leaving group has the highest priority. Our 2-carbon chain down here has priority number 2. The CH3 up there has carbon number 3, and then conveniently the lowest priority group is going back in the plane. So I think it's pretty obvious to you that you can just count 1, 2, 3, and you see that indeed this will be an R. On the opposite side, it is now that the nucleophile that has come in has the highest priority. This will usually be the case, that the leaving group and the nucleophile that comes in both will have the same high priority. We now have this 2-carbon chain as number 2, and then the methyl group as 3, and of course the hydrogen is 4 going back. If we now count 1, 2, 3, we'd see that this is an S. So we're going from an R to an S. By looking at that, you can see that it is an inversion of configuration. Now I will say that even if the carbon was not chiral, we'd still consider that this is an inversion of configuration, because you can see that in one case the leaving group is oriented on the right hand side, and in the other case it's oriented on the left hand side. So I will write that indeed this reaction represents an inversion of configuration, or we say a reaction has an inversion of configuration. Now again, remember that this will be true even if the carbon is not chiral. This is characteristic of an sn2 reaction, has an inversion of configuration. Another word about how I drew the original electrophile. Note I put the leaving group on the right hand side, and I find that most convenient. So even if your original molecule that you're given in an assignment or test is not drawn in that way, you may want to redraw the electrophile so it's oriented in this fashion, so that you can easily write out the mechanism as I've shown you here. It's good to get used to writing out the mechanism in a particular way. A couple of other points about this reaction. Okay, I'd like to represent the energy changes. So let me just grab my black pen here and make a little graph. And so on the left here I'm going to have energy, and then this will be the progress of the reaction. How about we just say progress? Okay, so as the reaction proceeds. And start off with the reactants. I'm going to draw this line here, and products. Now I'm not so interested in comparing the energy of the reactants to the products. So they may have different amounts of energy, and that would determine if the reaction is endo or exothermic. And maybe I just reproduce my hump here so that it looks a little nicer. All right. Now The difference in energy between the reactants and the height of this hump is known as the activation energy, the minimum amount of energy required for the reaction to occur. And as it turns out, the maximum amount of energy for this reaction is known as the transition state. It's the energy that's required for this reaction. The activated complex would be how the chemicals look like as they move through the transition state. Note that this reaction has one transition state. So we say actually that this reaction occurs in one step. So if it has one transition state, the reaction occurs in one step. And so let's emphasize that with one transition state, one activated complex. Okay, so one transition state. The other thing to mention, and this often confuses students, so it's the idea that it has only one step, but we say it's an sn2 reaction. This is because the reaction involves two things. Now, I'm going to use more fancy words in class, especially when we get to kinetics. One way to say that something has two things in the rate determining step, or in this case the single step, is to say the molecularity is two. But essentially it's got two reagents. And in this case the reagents are, of course, the nucleophile plus the electrophile. Okay, so we got the nucleophile and the electrophile, and they're both involved during the one and only step in this case, during the one and only step. Now you're going to see another mechanism where there'll be two steps, but in this case there's only one step. Now let's just verify. We'll come back up here. All right. So we say that this reaction is an sn2 reaction, right? Because it involves two things. Right? I know that's not a very scientific term, but perhaps you get the idea that it involves the hydroxide ion and it involves the electrophile. They're both involved in the one and only step in this reaction. So I've added some extra notes that would not normally be included if I were to ask you to write the mechanism. So just coming back up here, remember what I've written in blue essentially is showing you the mechanism. These are the rest of it are additional notes to help you understand better what's happening. Okay, so with this, let's now look at the sn1 reaction. So I'm going to draw a little bit of a line here to separate the two reactions. And maybe I go back to my blue pen, and at the top here we're going to say sn1. Now of course the S and the N still stand for nucleophilic substitution, but now we'll see why it's a 1. Okay, now I'm actually going to start off by writing the same electrophile. So the electrophile that we'll use will be the bromine leaving group. I'll have a 2-carbon chain coming down here. Note this is all written in the plane, so therefore I've got my CH3 group coming out and I have my hydrogen going back. Okay, now in this particular case I don't even need to write the nucleophile just yet. I have my leaving group just leave. That's going to be our first step. As a result, this is what we're going to form, and it's really important that you draw this correctly in the sense that it is a trigonal planar intermediate with a positive charge. Students often forget to include the positive charge. The leaving group is gone, so I'll just draw it here with a negative charge. Here's when our nucleophile is going to play a role. Now, I intentionally have chosen to use water, and you'll see a bit later in class why we're going to use water in this case. Now, just to make the comparison, let me come back up here and let's look at the sn2 reaction again. Note that in the sn2 reaction, the nucleophile had to attack from the opposite side of the leaving group. That's what happens in this particular reaction. And in part, it can only fit in there, and in a sense it bumps out the leaving group. But if our first step in the sn1, the leaving group leaves, we now have a trigonal planar oriented intermediate, and it means that the nucleophile can attack from either side. It's this nice accessible plane. Now I'll draw both arrows like this, and this is perfectly acceptable. Note that the arrows are starting from lone pair of electrons. I'm not implying that one water molecule does both attacks, but rather, in a collection of water molecules, we'll have one set of water molecules attacking from one side and one set attacking from the other side. Okay, so let's see the outcome of this reaction. And I draw a reaction arrow, and then I'm going to draw up and then down just so that we can separate the two possibilities. So in one situation, we can have the attack from the back. Okay, so just to make clear, this is what we mean by the attack from the back, the opposite side of where the leaving group was. And so now we've got the water molecule coming in, and the water molecule in fact has two hydrogens attached to it still. It's going to be making a new bond to our alpha carbon. We have the CH3 group still there, and we have the hydrogen going away from us. So that will be one of the products. Note, and try your best not to forget this, the oxygen here actually has a positive formal charge. Remember that oxygen normally owns 6 electrons, and in this case it only owns 5. So note, we're starting from a neutral water molecule, and when it starts to share one of its lone pair of electrons in making the bond, that changes the formal charge on the oxygen. Okay, so that's one of the possible products, but of course we can also have an attack from the front side. So I'll write front here. All right, this is meaning the same side as to where the leaving group originally was. And as a result of this, all right, so now I'm going to draw the water molecule on the front side. The oxygen is going to be making a bond to our alpha carbon. Okay, we still have that CH3 group coming out at us, and we still have the hydrogen going back. All right, there's still a positive charge on this oxygen. Now this is not to say that one electrophile gives rise to both of these products, but in a population of electrophiles, some will form the top product, some will form the bottom product. Let's explore these products a little bit more. So now I'm going to use my red pen again, and you might remember that we saw that the configuration for the electrophile was originally R. The configuration for the products we're going to have, now the priority will be the oxygen in the water, and then 2, and then 3, and then 4. And so counting, in this case 1, 2, 3, 4, we're counting counterclockwise, so that'll be an S, and this guy be 1, 2, 3, 4. So we're going to count in the opposite way, that'll be R. So you can see that we end up with both S and R. So there isn't overall a net inversion of configuration. In class we'll discuss the fact that this is referred to as a racemic mixture. So we actually have a name for when both enantiomers will form. And essentially this is a 50-50 mixture. Okay, so when we say a racemic mixture, we mean that both the S and the R will be formed in equal amounts. Okay, so a couple of other things that we need to comment on. Let's look at the energetics of this reaction. So now I'll turn to my black pen, make a graph here, where this will be the energy. Down here will be the progress of the reaction. Starting off with my reactant. And we'll look at the formation of the products. This time the profile is going to look different. We have our first transition state, we have a little dip, we have a second transition state, and now we have the products. Again, I'm not trying to imply that the products have less or more energy than the original reactants. That will depend on whether or not the reaction is endo or exothermic. We have our initial activation energy right here. So that would be activation energy 1. We also actually have another activation energy here. So that would be activation energy 2. We, in fact, have a couple of transition states. So that's a transition state. This is a transition state. So note the dip in the middle. This is not a transition state. And in fact, we label this as I. And this is I over here. What does I stand for? I equals the intermediate. So an intermediate is not the same as a transition state. An intermediate is a lower energy state that in some cases you might even be able to isolate the chemical, whereas in a transition state the activated complex is in between two actual existing chemicals. So you might be able to isolate this carbocation as being an intermediate spot in the reaction. There would therefore be a transition state, the first transition state, in going from the original electrophile to the carbocation. There would also be another transition state going to the other products. In writing an sn1 reaction, we don't write the transition states. You only need to write the intermediate. And in fact, the transition states, there's not much there to write. There's just the bromide leaving, and then of course the water, in this case, attacking. Okay, so let me point out to you that this reaction occurs in 2 steps. So unlike the first reaction that we looked at, where it only occurs in 1 step, this reaction occurs in 2 steps. And there are 2 transition states. But you know that this reaction is called an sn1. So this is because the reaction involves, this is the key here, one, and I'm going to use my fancy word, thing, or the molecularity is one thing during, and here's the key, rate determining step. So there are 2 steps. This first one is the rate determining step. This next part is step number 2. So step 1 is the rate determining step. And maybe it might be obvious to you that it's the step that has the highest activation energy. It's going to be the slowest step. It's the step that will determine overall the rate of reaction. And there's only one thing involved. And that one thing is just this electrophile. So this is why this is called an sn1 reaction. Now when we study kinetics, you'll see that this whole analysis will make more sense. So one thing is involved, and that's the electrophile. As you might remember, when we talked about the sn2, we saw that there were 2 things involved. So just coming back on the page here, both the nucleophile and the electrophile were involved in the one and only step, sn2 reaction. In the case of an sn1, only one thing involved in that first rate determining step. So again, what I've outlined in blue for the sn1 reaction is what you would typically write if I ask you to write the mechanism for this particular reaction via the sn1 mechanism. The rest of it are extra notes to help you understand the nature of the reaction.